or of a muscle cell. And you guys have now seen the neuromuscular junction and how that works, and the sliding filament theory. But now we're going to get a little bit more into that, what's really happening at the sarcolemma or the cell membrane of a muscle fiber. So we talked a little bit about that polarization of the cell itself. And so if the cell is considered polarized, then it is in a resting position. Nothing is happening, there is no contraction, and everything is good. So you can see that we have predominantly sodium on the outside of the cell. We do have potassium also, but we mainly have sodium outside, and then we mainly have potassium inside. When we're polarized, we have more positives on the outside. So you can see sodium and potassium are both positively charged ions, and they are both positively charged on the inside, but we have this other negatively charged ion on the inside that outweighs the positive charges. So that is what we're considering a polarized membrane. So as I said before, we mainly have sodium on the outside, potassium on the inside, and it says the sarcolemma is relatively impermeable to both ions, meaning that the ions do not move in or out freely. Now when we have the axonal terminal, and we have to remember what that is, that's where the axon and the sarcolemma come into contact. That axonal terminal is where all those synaptic vesicles are with the acetylcholine. So when the acetylcholine is received on the sarcolemma at the motor end plate, it changes so that the sarcolemma becomes permeable to sodium, meaning that the sodium is now going to be free to go into the cell. And remember that they always want to diffuse from high to low concentration, and so we had more sodium on the outside, less on the inside, so sodium is going to flow inside. And it's going to go through a channel or a protein. As sodium enters the cell, the resting potential is decreased because now we're not polarized anymore. We're becoming depolarized. So we're becoming, or we're changing the charges across the sarcolemma. And if the stimulus is strong enough, then we can have an action potential initiated. Now, as this depolarization event is traveling or propagating down the sarcolemma, and you can see it's traveling in one direction, it is unstoppable. And so once it starts, it can't be stopped. It will finish the entire depolarization event. And so we call this an all or none response, meaning that if the action potential starts, it can't stop. If we don't get the action potential to start, nothing will happen. So that's called the all or none. Now, immediately after the depolarization occurs in one direction, our body wants to stop the contraction, because this is going to cause a muscle contraction. And again, we don't want muscle contractions to occur continuously, or your muscles will fatigue. So what happens is the sodium channels close and potassium channels open. So we're going to now, all of the potassium channels are going to open so that potassium can go from high to low. If you remember, we had more potassium on the inside, less on the outside. So now the potassium is going to diffuse out of the cell. And what this does is it forms that polarized membrane again. However, the sodium and the potassium are on the wrong side. So now we have more potassium on the outside, more sodium on the inside, and we need the sodium to come back out and the potassium to go back in. So the repolarization is going to occur in the same direction. It's just going to follow the depolarization. And this has to occur so that the muscle can be stimulated again. So we're going to have this thing called a refractory period, where there's kind of going to be a resting phase. Now, The resting state is going to be restored by pumping the sodium and the potassium back where they're supposed to be. And pumps in our cells are fueled by ATP. You need a lot of energy for the pumps to work. So we're going to be pumping the sodium out, and we're going to be pumping the potassium back in to get it back to normal so we can actually rest. And again, this takes a lot of ATP to occur. Now, once generated, the action potential is going to propagate, which means it's just going to move in one direction. It's going to travel down the T tubules. So we're talking about one muscle is depolar, or one muscle fiber is depolarizing. And then as it goes down the T tubules, it's going to hit the next muscle fiber. And when it hits the next muscle fiber, because muscles are excitable, they're going to cause the next muscle fiber to depolarize, which then it travels down the T tubule, and then it will cause the next muscle fiber. So we call that coupling. And then calcium is going to bind to the troponin, and then we finally are going to have that sliding filament theory happen. And this is just, again, this one is just saying how that sliding filament is occurring, where the myosin cross bridges are attaching, and we are moving towards the center of the sarcomere. The sarcomere is actually getting smaller. Those Z lines are getting closer, and then finally calcium is going to be removed so we can relax that muscle. So this is what it looks like if we were to look at an action potential and the actual voltage that it takes. So you can see that this is a threshold, and the threshold has to be reached so that those sodium channels can open, because that's the very first thing that happens in depolarization. And then once that sodium starts to rush in, we hit the action potential, and the action potential is going to form, or going to cause those sodium channels to close. Then in order to depolarize, or that is the depolarization, I'm sorry. In order to repolarize, then the sodium channels are going to open, and we are then finally going to pump everything back and hit that resting phase where there's going to be nothing happening in the cell itself. So this is just going to be a series of pictures that are going to show you how everything looks when it is diffusing and getting into the T tubules and going down and making sure that all of the myofibrils are contracting. So we have our axon terminal, we have our motor end-plate, we have the acetylcholine that's going to diffuse across, be received, and then we're going to, here's where we initiate the action potential. So sodium is going to enter, and we're depolarizing all the way down the sarcolemma, and right behind it we're going to be repolarizing, and then it's going to go down the T tubules. And these T tubules are really important because it's going to get to that next fiber so we can get deep into the muscle itself. Calcium is going to the action potential. As the T tubules are depolarizing, the calcium is going to be released from the sarcoplasmic reticulum, the cisternae of the sarcoplasmic reticulum, and then this is where all of the events of the sliding filament occur that we've learned about already. So we're going to have the contraction, we're going to remove the calcium, we're going to then get back into our resting potential.